Hello everyone. Today we will discuss binary relations, and more specifically we will talk about the properties of binary relations. This is part of Discrete Mathematics lecture. Okay, now let's start with the definition of binary relations. A binary relation R between set A and B is a subset of the product Cartesian of A and B. So some of the members of the Cartesian product of A and B, or maybe all of them, will be the member of the relation R. So relation R is actually a set. So R will contain the this pair A B, something like this. But there will be several members, and the members is also the member of this Cartesian product. We usually use this notation ARB. It means that AB is the member of set R. It means that A is related to B by relation R. If A is not related to B by relation R, then we will use this kind of notation. But actually, it should be the line here should be something like this, similar to this notation. With regard to this relation, then set A is referred to as the domain of R, and set B is the range of R. It is also possible for us to only work on one set. So for example, we have a relation that relates a member in set A and a member in set A. So it will be the subset of the Cartesian product of A and A. These are examples of binary relations. Suppose we have set B here, contains 2, 3, 4, and then Q contains 2, 4, 8, 9, 15. We can define a relation R from P to Q with this characteristic. So P, Q elements of the relation if P divides Q. If we use this, since we use these two sets, then we will get R. R contain these members. 2, 2, because 2 divides 2. 2 divides 2. Then 2, 4. 2, 8. Yeah? And then 3, 9. Yeah? 3, 9. And then 3, 15. And then 4, 4. 4, 8. Yeah? Those are the members of relation R. Yeah, as we can see here, the members of R here is a subset of P cross Q. Yeah. And as I already mentioned previously, relation on set A is a subset of A cross A. One of the representations of relation is by using a matrix. This is only one of the representation. We can also use, for example, a kind of graph, digraph. Yeah? So but we only focus on this representation using matrix. Yeah, so if we have R is a relation from A to B, then we can represent the relation R as matrix M. Yeah, M each contains elements Mij as follows. Yeah, so we have here the matrix, and the row here refers to the element in the first set, yeah, A1, A2 to AM, and then the column here refers to the element in set B, P1, P2 to Pn. The element here only consists of 1 or 0. It will be 1 if AIBJ is the member of R. It means that AI is related to BJ. It will be 0 if AIBJ is not the member of R. It means that AI is not related to BJ. We can also use a table here to represent the relation. I think the logic is the same. It's just that we use a table here instead of a matrix like this. Now this is the main topics that we discussed today. Properties of relations. We can define 4 properties of relations here. The first one is reflexive, transitive, symmetric, and anti-symmetric. So in this case, a relation can have these properties or not. So actually this will be the basic of properties to determine whether the relation is an equivalent relation or maybe a partial ordering. It doesn't mean that each relation has all of these properties. So a relation can be either reflexive or not reflexive, can be either transitive or not transitive, can be symmetric or not symmetric, and can be anti-symmetric or not anti-symmetric. Okay, we will discuss each of the properties here. The first one is reflexive. Relation R from A to A is reflexive if A element R for all A element of set A. So in this case, for each of the member of element of set A here, A element of set A here, then it will be related to itself. A means that A is related to A. Yeah, of course, A should be the same here. A equals to A. So this is the reflexive property means. We will see the example later on. Relation R in A is not reflexive if there exists A element A such that A is not the element of R. It means that there is at least one element in which it's not related to itself. Okay, so these are the examples. Suppose we have A here, 1, 2, 3, 4, and R is defined on A, means that R relates a member of A to a member of A as well. The domain and the range of R is A. Suppose we have the first relation here, 1, 1, 1, 3, 2, 1, 2, 2, 3, 3, 4, 2, 4, 3, 4, 4. Yeah, if we examine this relation here, then we can see that for each of the member of A, it will be related to itself. Yeah, so we have here 1, 1, and then 2, 2, 3, 3, and 4, 4. So 1, 1, 2, 2, 3, 3, 4, 4 are elements of R. This kind of relation is a reflexive relation. On the other hand, if we have this relation 1, 1, 2, 2, 2, 3, 4, 2, 4, 3, 4, 4, yeah, on A, then we can see that at least there is one element here that is not related to itself, because here 3, 3 is not the element of R. 3, 3 doesn't exist here. So it means that relation R is not reflexive. Another example, relation divides, yeah, on the set of positive integers is also reflexive because every integer divides itself. Yeah, so A is related to A. Yeah, so 1 divides 1, 2 divides 2, yeah, 6 divides 6. A is related to A. A divides A for all A element of set A. We can identify whether a relation is reflexive or not using the matrix representation of the relation. So this is the characteristic of a reflexive relation. The main diagonal of a matrix that represents a reflexive relation contains 1. So we will have this kind of matrix here. Yeah, the main diagonal is 1, 1, 1, 1, 1. So MII must equal to 1 for I from 1 to n. Yeah. Okay. The next property is transitive. Relation R on A is transitive if AB element of R and BC element of R, then AC is also the element of R. ABC is the element of set A. So yeah, it is just the common transitive property, but in this case we apply it for relation. Yeah. So if we have AP and BC on R, then AC should be also on R. That's the transitive relation. Okay, suppose we have this set and R is defined on A. If we have this relation, then we need to check one by one whether the relation is transitive or not. Okay, 2, 1, 3, 1. I think we cannot have the second relation here, 2, 1, 1 something. There's nothing like that. But for 3, 2, then we have the second relation here, 2, 1, 3, 2, 2, 1. So the transitive will be 3, 1. And 3, 1 is also here. 3, 2, and then 2, 1, and 3, 1 is also here. Then 4, 2, 2, 1, 4, 1 is also here. 4, 3, 3, 1, 4, 1 is also here. And we have also 4, 3 here, 4, 3, then 3, 2, 4, 2 is also here. So this is a transitive relation. Then this is a transitive relation. Suppose we have another relation here, 1, 1, 2, 3, 2, 4, and 4, 2. It is not transitive because we have here 2, 4, and we also have this one. We also have 4, 2. If it's transitive, then 2, 2 should also be in the relation, but there is no element 2, 2 here. So in this case, R is not transitive. It is also the same for this one. Okay, the next one here is 1, 1, 2, 2, 3, 3, and 4, 4. Since actually there is no the member here, the second member here, the second relation here, so the second pair here is not available. So by default, this is also transitive, even though we cannot have, because there's nothing like this one, 3, 2, 2, 1. It is always by the member, then the element here is always related to itself, 1, 1, 2, 2, 3, 3, and 4, 4. There's no other type of relation. So by default, it is transitive. And relations that consist of only one element, like this one, 4, 5, is always transitive as well. So these two are by default transitive relations. These two, the last two here. Then relation divides on the set of positive integers is also reflexive. This also should be transitive. Suppose that A divides B and B divides C. It means that here there exist integers m and n such that B equals to ma, because A divides B, and then C equals to mb because B divides C. If we replace here B with ma, then we will have C equals to m and a. It means that A also divides C. So that's why if A divides B and B divides C, then A also divides C. So divides, relation divides here is transitive. Unfortunately, there is no specific characteristic of the matrix representing a transitive relation. So we cannot identify whether a matrix is transitive or not using the matrix. But if there is another way, if we use the diagraph representation of a relation, then at least we can check one by one whether the relation is transitive or not using the edges that represent the relation. The next property is symmetric. So relation R on set A is symmetric here if AB element R, then BA is also element R for AB element of set A. So if AB is the element of R, then BA should also be element of R. R on set A is not symmetric. This is not anti-symmetric, so not symmetric if there exists a B element R such that BA is not the element of R. So this is the examples. We have R. R here means the relation R here between X and Y. It means that X is larger than Y. Then we also have the second relation here, S. X plus Y equals to 6, and T, 3x plus Y equals to 10. The first one here, R is not symmetric, because if X is larger than Y, then Y is not larger than X. Yeah, this is an example here. 5 is larger than 3, but 3 is not larger than 5. So 3, 5, 3 is the element of R, but 3, 5 is not the element of R. The second relation here, relation S, is symmetric, because if x plus y equals to 6, yeah, then y plus x is equals to 6 as well. So xy and yx are always members of S, no matter what the value of x and y are. And then for this one, T is not symmetric, yeah, because for example here we have 3, 1. 3, 1 is a member of T, so 3 times 3 plus 1 equals to 10. But of course 1, 3 is not, yeah, because here 3 times 1 plus 3, that's only 6. So 3, 1 is a member of T, but 1, 3 is not. The matrix that representing a symmetric relation will be a symmetric matrix. So it will be a kind of mirror using the main diagonal of the matrix 1, 1, 0, 0. If we have here 0, the corresponding element here should also be 0. If we have 1 here, then the corresponding element is also 1, should be 1. Yeah, so Mij equals to Mji equals to 1. Yeah? For ij equals 1, 2, 2, n. Yeah, so if Mij equals to 1, then Mji must also equals to 1. But if it is 0, then Mji should also be 0. The last property is anti-symmetric. Again, it doesn't mean that it is not symmetric. Yeah? Anti-symmetric doesn't mean that it is not symmetric. Yeah? So these are two different properties. Yeah? We have to check whether it is symmetric or not. Yeah, still. Yeah. So not symmetric doesn't mean that it is anti-symmetric. Not anti-symmetric doesn't mean that it is symmetric. So you have to keep in mind the differences between symmetric property and anti-symmetric property. Okay, relation R on A such that AP element A and element R and PA element R if and only if A equals to P. That's the meaning of anti-symmetric. So AP element R and PA element R if and only if A equals to P. Otherwise, yeah, if A doesn't equal to P, then if AP element R, then PA should not be element of R. Yeah. That's the meaning of anti-symmetric. Yeah, so AP element R, then PA element not element R, except if A equals to P. Okay. Relation R on A is not anti-symmetric if there exist different elements A and B, means that A doesn't equals to B, such that AP equals to R and AP elements of R and PA elements of R. Yeah, so if there exists something like this, AP and BA both are elements of R, and A doesn't equal to B, then R is not anti-symmetric. Okay, we will see the examples here. Suppose we have A here, 1, 2, 3, 4, and then we have R. R is defined on A. Yeah. Relation 1, 1, 2, 2, 3, 3 here is anti-symmetric, by default actually here. Anti-symmetric because 1 equals 1 here, and 1, 1 element of R, and then 2 equals 2. 2, 2 is also element R, and 3 equals 3. 3, 3 is also element R. So this is by default is anti-symmetric because the elements here only consist of the relation, yeah, from an element here to itself. Yeah, and if we can see here, R is also symmetric. So this relation is both anti-symmetric and symmetric. Okay? It is of course symmetric. Yeah? 1, 1, 1, 2, 2, 3, 3. 1, 1, 2, 2, 3, 3. It is symmetric by default, and it is also anti-symmetric by default. Okay, the second one here, relation R. 1, 1, 2, 4, 3, 3, 4, 2. We have here 2, 4, and 4, 2. Yeah? So it's not anti-symmetric because we have 2, 4, 2 doesn't equal to 4, yeah? But 2, 4, and 4, 2 are both members of R. If it is anti-symmetric, then if 2, 4 is the member of R, then 4, 2 should not be the member of R. Then we also have here 1, 2, 2, 3, 1, 3, and this is also anti-symmetric. 1, 2 is the member of R, 2, 1 is not the member of R. 2, 3 is the member, 3, 2 is not. 1, 3 is the member, 3, 1 is not. Yeah. But this is not a symmetric relation, yeah, because we have 1, 2, but 2, 1 is not. Yeah? 2, 3, 3, 2 is not. Okay, the last one here, 1, 1, 2, 2, 3, 3, 2, 4, 2, and 4, 4. This is not anti-symmetric nor symmetric. Yeah? It is not anti-symmetric because 2, 3 element of R, and 3, 2 also element of R. 2, 3 and 3, 2 are elements of R, but they are not the same. They are not the same. So R is not anti-symmetric. Yeah. And it's not symmetric because we have 4, 2 here, but 2, 4 is not the member of R. Yeah. So R here is not anti-symmetric and not symmetric. Okay, other examples we have like in the previous slide, R. R is means that x is larger than y. Then we also have s, x plus y equals to 6. R here is anti-symmetric because if a or if x here is larger than y, then y is not larger than x. Yeah. So if a is larger than p, then p is not larger than a. Yeah, that's using the logic. Yeah. If a number is larger than another number, then the other number is not larger than the first number. So R is anti-symmetric. S here is not anti-symmetric because we have 4, 2 and 4, 2 and 2, 4. Both 4, 2 and 2, 4 are elements of S, but 3 doesn't equal to 2. Now, in fact, actually, S is symmetric, because if we have x, y elements of S, then yx is also the element of S. Other examples, again, relation divides on the set of positive integers is anti-symmetric, because if A divides B and B divides A, then A should equals to B. So a number here, a positive integer here, will be divides itself. Will divide itself. But if A and B are not the same, they are not the same number, then if A divides B, then B doesn't divide A. So, for example, 2 divides 4, but of course 4 doesn't divide 2. So it will this happens only if A equals to B. For example, 4 divides 4, 3 divides 3, and so on. So divides here is anti-symmetric. It is not symmetric because if A divides B, B doesn't divide A, except if A equals to B. So for example, 2 divides 4, but 4 doesn't divide 2. So it means that it's not symmetric, because for every AP element R, then PA is not the element of R if A and B are different numbers. And this is the representation of matrix that representing an anti-symmetric relation. If Mij equals to 1, if I doesn't equals to j, then Mji must also equals to 0, must equal to 0. So we have here, if this is 0, then the corresponding element here is 1. If it is 1, then it should be 0, 0, 1. It's always like that, like this, like that. So we cannot have something like 0, 0 or 1, 1. We cannot have something like 1, 1 here. Okay, yeah. I think that's it. The properties of binary relations. Thank you for watching, and I will see you again in the next video related to discrete mathematics. Thank you.